Hello everyone, welcome back to the Direct Access 1.0 Music Production Workshop. Thanks again, I'm really excited and we're going to continue today. This is week 2, alright? Alright, so let's kick off first of all, properties of sound. So, us being music producers, audio engineers, we have to understand the medium that we are working with. Ultimately, music, be it instrument, be it vocals, anything, we are dealing with sound. We're dealing with sound waves. So, it's important to understand the properties, right, of sound because it helps us understand a lot of things. It's related. The knowledge of how sound behaves and how sound reacts is very applicable to your recording skills. It's going to be applicable to mixing skills. It's going to be applicable to even your arrangement. It's really applicable to everything. It's not just science and information. Even live sound, right? It's going to be applicable as well. Live sound, I think, is even more important to understand the behavior of how sound behaves. Okay, so let's get into it. So if you go into a dictionary or if you go into Wikipedia, you go into encyclopedias and all that, right, you find several definitions, right? They have different definitions. So number 1, vibrations that travel through the air or another medium and can be heard when they reach a person's or animal's ear. So that's the definition of sound. Okay, now this is actually kind of a combination of different definitions, because if you ask a scientist, right, or a technical person, they give you this definition. But you ask a sociologist or you ask someone who's coming from a more social science background, they will give you a different definition. So this is a combination of the two. First part, right? Vibrations that travel through the air or another medium, right? So, right, it can be another medium, it can be solids, right? It can be liquids, okay? All right, not necessary to air, which is a gas. The second part of the property of sound, it's something that can be heard when they reach a person's, right, or an animal's ear. Sound, very importantly, sound requires a medium, okay? So medium, it means it needs some sort of material to travel through. So it cannot travel in a vacuum, right? In the vacuum of space, or for example, if you ever back in science, your science lessons, you remember the experiment, where they put the alarm clock, a bell inside a jar, and then they slowly pump out the air. Suddenly you cannot hear the alarm. The alarm goes softer and softer until you cannot hear it. That's exactly the demonstration that sound needs a medium. It cannot travel in a vacuum, okay? Just for your general knowledge, so the speed of sound, this is stuck very fun, and the definition according to science, you must always have a reference. You must always qualify something, okay? And that's very important later when we talk about decibel, when we talk about dBs. You always need to qualify and reference it to something. So now, speed of sound is 343 meters per second in, right, dry air at 20 degrees Celsius, okay? Right, if it's humid air, there's a lot of moisture in the air, speed of sound also travels differently. Temperature also affects it, right? Cold, right, temperatures, the speed of sound is a little bit different, right? Warmer air also, it's a little bit different as well, right? So this is a scientific figure. But for ease of calculation, to make calculation easy, right, most of the time, for laypersons and laymen, when we calculate, right, we round it down to about 330 meters per second lah. Knowing this fact, okay, 330 meters. So next time, when there's a thunderstorm in KL, right, just like how we had the floods, right, this week in KL, okay, terrible floods, right. So next time, if you hear a thunderstorm and then you see the lightning in the distance, okay, you try and count, right? Immediately count. You see the lightning, you try and count. 1, 100, 2, 100, 3, 100, 4, 100, 5, 100, 6, 100, boom, right? Then you hear the thunder, right? So 6 seconds. Can anyone guess how far away is the lightning? If the thunder takes 6 seconds to reach you. 1.8 kilometer. Wow, okay, great. That's good, right? So if you narrow it down, that would be 990 meters per second times 2 would be 1880. Yeah, it's about 1.8, 1.9 kilometer lah. So lebih kurang 2 kilometers lah. We just say 2 kilometers, okay? So we know, right? It's 2 kilometers away. 1,000, let's go again. So this is again scientific definitions lah. 1,481 milliseconds in fresh water at 20 degrees Celsius. Now when it goes through water, it's a much more dense medium than air. Sound waves travel a lot faster. If we look at a solid steel, for example, it's 5,790 meters per second. That's like 5.5 kilometers, 5.75 kilometers per second. That's how fast a sound wave can travel through steel, right? So through solids, it's even faster. Now, let's talk about a couple of other things as well. So we hear the word ultrasound, right? Everyone knows, right? Ultrasound, especially it's very common now for in the medical world. So ultrasound here, the definition of ultrasound, these are sound waves with frequencies higher than the upper audible limit of human hearing, right? Remember last week I talked about what's the human hearing range and why that's related to sampling rate. So you see, again, everything is connected. Why, bit depth, why sampling rate, it's all connected as well, okay, to all this information, the human range, the range of human hearing and all that. So ultrasound would be, right, anything that's higher than 20 kilohertz lah, right, even up to several gigahertz as well. That's also possible. Okay, now infrasound on the other hand is the opposite end of the spectrum. So these would be sound waves which are like equal or lower than, right, or lesser than 20 hertz. So these are like really infrasound sound waves already, right? Really low frequencies. Right, let's move on to the next slide, right? Subjective versus objective properties. Okay, so before that, that's the technical scientific definition of sound, right? Sound also can be defined in like subjective and objective ways, okay? So right, here's a very it's a very famous quote, it's a very famous phrase, right, that you find. If a tree falls in the forest, but nobody is there to hear it, does it make a sound? From a technical and a scientific point of view, yes, it makes a sound, right? But if there's no one or no living creature around to interpret and to hear and define a sound, is there sound then? You see? Okay, now, I don't have an answer for this, so this is a more of a philosophical kind of question, you see. So, now a layman, an average person, okay, they describe sound in a subjective manner. It's important to understand this also because later on, if you are producers and when you are, if you are an engineer and you're dealing with clients, you're dealing with artists, you have to understand that a lot of times they will look at it from a very subjective manner. So you need to understand both the subjective and objective properties of sound. So layman describes a sound in a subjective manner that's based on their perception, how they perceive it, how they hear it and they perceive sound in a certain way. Musical sound. So it has got these subjective sound properties, okay? It's got your pitch, it's got your timbre, and loudness, okay? So these are the three subjective, right, sound properties. It's based on how our ears perceive the sound. When you start using electronic technology, you start using scientific measurements, right? Meters, you start using meters, measuring microphones and all that. We can also describe this sound, right, using objective sound properties. So objective means you can measure it. You can measure, you can analyze. So when you use that, all right, what you can get, you will define the properties would be frequency, number one. The number two would be the spectrum or wave shape. And number three, the intensity, right? Or / you can also refer it as the amplitude lah. These are actually the same. These three properties are the same, but it's described differently. You ask a layperson, this is how they describe. They describe it as the pitch, the timbre, and loudness. But you ask a technical person, they will describe it as frequency, spectrum, and intensity, right? So it's actually talking about the same thing, but looking at it, right, in different ways. Subjective or objective. Right, let's move on to the next slide. Pitch and frequency, okay? So remember, pitch is the subjective property, frequency is objective, okay? So we tune an instrument, okay? We tune our instruments by matching the pitch, right? What note it is, right? To some tuning reference, okay? For example, A above middle C, that is what the standard tuning frequency is, or A equals 440. 440 here is 440 hertz. That is the sort of the ISO standard. So 440 here, it represents a frequency standard, right? This is defined by the ISO, right? The International Standards Organization. So meaning that a sound that vibrates 440 times a second is equal, right? It's equivalent to the A, right? If you have a piano with you, a full range piano, the A note above the middle C on our musical scale. So we judge the pitch, right? From our hearing, a layperson, we judge it, we judge the pitch, but we can measure the frequency. So you see these two differences, subjective and objective. Obviously, a high frequency, you can see there's more vibrations within the same time period. Low frequency, right, you have fewer vibrations within that same time period. This is logical common sense, right? Okay, let's move on. Next one, still talking about pitch and frequency. So pitch sound is a periodic, all right? Periodic means that, in Malay, in BM, it's called berkala, right? That means it always repeats in a pattern. There's a pattern to it. So it's a periodic phenomenon in which a particular vibration pattern repeats regularly. So that's what we mean by periodic. The frequency itself, right? The word is defined as the number of times that pattern repeats. And as we all know, it's expressed numerically in the unit hertz, okay? Right? Or HZ, hertz for short. Now, in the old days, in the outmoded terms, right, they used to refer it as cycles per second, CPS, right? If you look maybe some very old documents and old papers, right, maybe we'll still have CPS, but nobody uses that. Everyone uses hertz nowadays. Higher frequency, right, is generally heard as a higher pitch, Okay, that's natural. That's good. And the reverse is also true, right? Lower frequency is heard as a lower pitch. Modern pitch standard is A4 equals 440 hertz, as I explained earlier. All right. So a couple of other things, all right, that's kind of interesting to know, right? Kind of interesting to know about pitch and why the subjective and objective can be a little bit different. So scientifically, right, if we look at octave, right? Everyone knows what an octave is, right? Right. So you have, let's say, middle C, and then the C, which is above middle C, do, okay, that would be defined as a 2-to-1 ratio. So for example, if we take the A, A440, now if we go one octave higher, frequency wise, if you measure it, okay, it should be twice that, it should be double that, that should be 880 hertz. But there's a very funny thing when we talk about the musicians and the human hearing. It does not always judge. We don't always perceive that interval of an octave at that same 2-to-1 frequency. So if we hear and if we just tune using that figure, right? But if we tune it by ear, you get the result is slightly different. Now, for example, right, when it comes to piano, right, certain instruments, right, there's something called stretch tuning. So stretch tuning means that, as it kind of goes higher into the range, higher into frequency, the ratio actually gets stretched a little bit wider. And so that's why when it comes to piano, right, piano tuners are a very, very specialized job, right, because they also have to do it by ear. They cannot just rely on a meter. If you rely on a meter, everyone also can become a piano tuner. Everyone can also become a tech. Some of these things you still need to rely on ear, by ear, right? It has to be trained, it has to be built, it has to be development. So what this means here is that we actually, as human beings, we perceive pitch in a non-linear, right? It's a non-linear response to frequency. It's not a straight line. It's not exactly right to how we measure it. It's important to know it is not. It's important to be aware of that as well. Because even with guitarists, fretted instruments especially, right? You always know guitars always have the intonation issues and all that. We kind of be aware of that. Sometimes if we are dealing with very, very high extreme range, you sometimes have to tweak the tuning a little bit. You ever encountered that situation, guitarist, right? Especially if you're playing, guitarist is playing a part that's high up. Sometimes we have to tweak the tuning. Okay, so let's move on. This is the second property of sound, the timbre or the wave shape / spectrum. Okay, so timbre here. This lets us tell apart one instrument from another. A instrument's timbre helps us determine, oh, this is the sound of a piano. Oh, this is the sound of a violin. This is the sound of a guitar, right? Even though it's playing the same note. So how a note starts and ends also helps judge what kind of instrument is involved, lah, right? So if it's like a guitar, or or it's a drum, you have a or a piano, you have a very defined transient, right? You got a very clear attack. But when it comes to a violin, for example, a bowed instrument, or if let's say even when you talk about guitar, using a pick versus using fingers, right? It's different. The note, how it starts, the attack, the transient, right, also defines, it helps us identify, oh, this is the sound of a certain instrument, this is a different sound. So transient behavior involves the attack and release, all right? Oscilloscope, right, very quickly. So it's a device that can, right, graph and chart out, right, dynamically graph the sound pressure level, right? SPL is going to be very, very important, right, as it changes in your time and displays a distinctive wave shape, okay? So if you look at an oscilloscope, you have your time defined by a horizontal, okay, by a horizontal left to right, and your amplitude, your vertical, up and down. There are actually 4 basic waveforms, right? All kind of sounds that we hear can actually be defined and broken down and categorized into these 4. Sine wave, as you can see at the top, which is the simplest and the most pure wave there is. There's the square wave, right? So square wave is, as you can see, looks like a square lah, right? Then you have the triangle, and lastly you have the sawtooth. Sawtooth is like a triangle except that it's sengit, right? So sawtooth looks like the mata gergaji lah, okay? Sawtooth. Anybody here who is playing a lot with synths and synthesis, right, will know that this is like really basic for them. Okay, this is the basic sound waves that are there. Now, still sticking with timbre and wave shape. So sound can also be represented in the frequency domain. Okay, well, that's obvious lah, we know. Okay, now there are differences among various static or steady state wave shapes. So the difference between, right, all those 4 basic wave shapes, right, even though when you listen to them, right, when you hear it inside with the studio monitors, it's going to be very clear. So the differences, even though they may be playing the same frequency, even though they may be playing the exact same note, we can tell the difference, right? It's because of their spectral content. The spectrum of a particular wave shape, right, comprises many simple components called partials. Again, this is a lot more technical already. You don't have to remember, don't have to memorize this lah. It's just general knowledge for you, okay? So, as I mentioned earlier, the sine wave, right, is a pure sound, okay? So that's actually the pure and the most simple wave, right, that's out there. The square, sawtooth, and a triangle, those are all modifications, right? If you apply, certain filters and all that to a sine wave, you will derive all the other basic wave shapes lah. So remember, sine wave is the most pure sound. Okay, now, so just for example, what do you mean by partials? How we can identify, for example, that, oh, it sounds like a cello, right? When a cello, for example, is playing G sharp on the D string, right? So C, G, D, which is the 3rd string on the cello, and he plays a G sharp note up there, okay? Right, so not only can we identify the cello is playing the note G sharp, okay, which is indicated by the very first spike that you can see, right, the very first peak, that's your G sharp note. But you also have your harmonics, all the upper harmonics, right? So these contributes to the spectral content of what we hear as a cello sound, okay? So you have, spikes in between there, right? You have another spike between 500 and 750, then a slightly higher one, that will be your 3rd harmonic, and so on and so forth, lah, right? It gradually goes weaker, right? But all these spectrum contents, all these overtones, all these harmonics, right, that we refer to, helps us identify, oh, okay, that sounds like a cello playing the note G sharp. Let's move on. Okay, all right, okay. Now, when we listen to all the normal sounds that were musical instruments, right, that we hear every day, obviously, right, we don't hear sine waves all the time, okay? The waves that we usually hear, okay, especially when it comes from musical instruments, is actually usually it's a complex wave shape. It's usually a complex one, right? So it always consists of the first partial that we call the fundamental, right? So again, going back, the fundamental note, right? In this case, in this example, is the G sharp, the root note lah, okay, the fundamental note, and the other partials, right, of the higher frequency and smaller, right? It's always softer one. All the overtones and harmonics, right, will always be a little bit softer and usually higher frequency. Okay, now again, very, very rough general knowledge. Don't have to memorize any of this. When you have a whole number multiples, right? Right, whole number multiples, right, means that you times 1, times 2, multiply by 2, multiply by 3, right, of the fundamental note. This is what we refer to as harmonics, okay? Right. So guitarists, right, will know lah what the harmonics are and all that. Anyone who plays string instruments will know what harmonics are. So for example, if a fundamental of 100 hertz, you have harmonics that will happen at 200, 300, 400, 500, 600, so on and so forth, okay? So the presence and strength of all these harmonics, right? The harmonic spectrum influences our perception of the timbre. So again, going back to the example of the cello, right? All these harmonics that happen tells us, oh, this is the sound of a cello. This is the sound of a guitar. This is the sound of a piano. This is the sound of a trumpet, for example. Okay, now when it comes to non-integral, okay, non-integral, right, bukan not an integer lah, okay, right. So if it's not a whole number multiple, for example, if it's times 1.5, right, or it's like times 2.24, for example, so it's not a nice round number, right, you get non-harmonics. So for example, you have 100 hertz, then you have 215 hertz, okay, that's the non-harmonic, right? Then you have 300, you have 400, and then you get 550, for example, right? So be aware. So some of these non-harmonics, it can be a tip for you to know this. And when I say it's general, actually it's important also when it comes to mixing, because these non-harmonics don't contribute to the sound in a pleasing way, right? Right, we kind of hear it as the alamat. This is like the very harsh, very clashing overtone. We like to call it. It's kind of a dissonance. We can hear this kind of dissonant sound. So if you can know how to listen to it and identify this helps you when it comes to mixing as well. Okay. All right. Now, so what happens when you get, right, all these partials, all these harmonics? You get all these frequencies distributed randomly over the entire hearing range. Okay, that's what we call and define as noise lah, right? When everything is random, right, it's called noise. An interesting side note, okay, if you ever in a mastering project, if you take a whole album and you take all the tracks, let's say 10 tracks in the album, you load it up inside your CP, your DAW, you turn the volume down first because it's going to be super loud, and you press play, all 10 tracks. When they start playing, you know what it sounds like? It sounds like in a market. It sounds like, you know, it sounds like random noise. Okay, so that's very interesting, right? Try it for fun someday. Okay. Okay, now moving on. This would be the third property of sound. Okay, first one we talked about was the pitch and frequency. Second just now was your timbre or your spectrum, wave shape. Third one, loudness, not the band, okay, not the Japanese band, okay. Loudness, right? Loudness is again the subjective, right? The intensity or amplitude is the objective that we can measure, right? So the amplitude, right, and the objective sound property of intensity, right? So amplitude, right, which is intensity, it's related to the subjective sound property of loudness. We can measure the intensity, right, of sound using devices like, for example, an SPL meter, right, sound pressure level meter, using the decibel scale, right? So nowadays you even have SPL meter app on your phone already, okay? It's very, very easy. Everyone can have a SPL meter, right, on their hands. I love doing that because going anywhere, it's like I tweet, hey, okay, I want to see what's the SPL of the room or the place that I'm in. Where you go, you sit in a car, you sit in the MRT. Okay, you switch on. Oh, right, interesting. So that's the SPL level inside the MRT. Right, so now if you take an oscilloscope, right, the signal amplitude level is measured and expressed in the units of volts, lah, okay? Right, general knowledge. Okay, now, here's a very important point, and the next point I want to talk about is this one you have to understand very, very clear. This one is important, right? Human hearing, right, is non-linear. This is very important to understand, right? Okay, so why is that, right? So the loudness when we perceive something, right, how loud or how soft something is subjectively, it can vary, right? It can vary, even though, and this is very important, even though the objective signal amplitude does not. Okay, let me sort of repeat this again, right? So the loudness, we perceive something, right, how loud it is, it can change, it can subjectively change. Even though if we take a meter, we measure it, right, but that it stays the same. But our here, right, is non-linear, right? It can change. And this is described by this little phenomenon. Very important. Okay, this is called the Fletcher and Munson curve. You guys ever encountered and heard this term before? Very important. You're dealing with sound, you need to be aware of this, right? All right. Whether you are a musician, whether you are an engineer, you need to be aware of what this is. Okay. So now there are actually several other curves. We refer to this graph here, okay, as the equal loudness contour or the equal loudness curve. Okay. So the most famous one and the one that most people refer to is the Fletcher and Munson curve. Okay, now, so let's take a first. Let me just sort of lay out this little graph, because some people, when you look at graph and numbers, it gives them flashback of their maths and your science class back in secondary school. So people like there's some panic attack. Okay, right. So take it easy. So now on your horizontal, okay, on your x-axis, this is your frequency lah. Okay, so frequency from 20 all the way to 20k. Okay, human hearing. Now on your left, on your y frequency, your vertical is your sound pressure level, your SPL level. So very easy lah. Frequency versus your SPL, how loud the intensity of the sound is. Now the lines here, right, are all, each line is a specific loudness curve, and you can see that it's a curve. None of it is a straight line, right? Okay, because again, as in the previous point, right, human hearing loudness is not, we hear it in a non-linear function. Actually, earlier when I was talking about pitch is also non-linear, right? So human hearing is a very funny thing. So loudness also is also non-linear. So each of these is a specific loudness curve at a specific phone level. Okay, so phone level, roughly we're talking about dB lah. Okay, so all right, phone here is the subjective perception, right? So when we perceive something that sounds like about 10 dB, we end up with this. We end up with this solid line. Okay, now the dotted line here is the threshold of audibility. That means, right, a threshold of audibility here means that our human ear, that's like kind of the lowest that we can perceive the sound. Below that, we cannot hear already. We can't hear, but sometimes on the meter you can still it will still detect. Right, on an oscilloscope or an SPL meter, it will still measure it. Now, looking at all these curves, there are a couple of things that we want to be aware of. That looking at this pattern, right, you can sort of see it generally tends to curve upwards. Where? Towards which range of the frequency? Towards the lower end, and actually also slightly towards the high end, right? So our frequency curve, our frequency, our hearing, right, response, right, our frequency response of our hearing tends to skew upwards towards the lower frequencies and also towards the high frequencies. Maybe that's why we all love to always have the smiley curve EQ lah, right? That kind of EQ, right? The smiley face EQ, right? Because our human ear tends towards that. Okay, now what this means by this curve. So for example, let's take for example the bottom one lah, right? If something is at 10 dB, okay, which is super soft, like you almost cannot hear it. To hear something equally loud, right? So for us to say that, oh, it's the sound, same loudness, we actually have to turn up. If let's say 50 hertz, 50 hertz goes up to 50 hertz is roughly 45 dB. That's a huge difference. There's like a 35 dB difference in value, right? So a frequency that's at 50 hertz, for us at the human hearing to hear it as the same loudness as something let's say at 1 kilohertz, right, 1000 hertz, you need to turn that bass frequency up by 45 dB. That's a lot, That's 45 dB. So to hear something, or so to hear a frequency, right, let's say 50 hertz, to hear it, to perceive it as the same loudness, right, of a sound that is at 1K, the difference is very big, right? That's like 45 dB difference, right? And then same goes, looking at the graph. If we have a sound at 10 kilohertz, 10K, to hear it at about the same volume level, we are talking about, okay, not as drastic lah, right? But that's about maybe 18 dB. But still, 18 dB is a lot, right? If you know, right, in mixing, you put something up, boost something up 1 dB or so, right? Oh, right, it makes a very, very huge difference, okay? So 18 dB, 20 dB difference, right? If we hear a sound at 10 kilohertz, only there we perceive it. So understanding this, right? Understanding how a human ear, right, helps us to understand, right? When we talk about frequencies, when we talk about our mixing, when we talk about our arrangement as well, right? So it's very, very useful. Now, a couple of things that you can also derive from this chart. Now, these are all curves lah. They are definitely not flat. But there is actually a certain range. Okay, there's actually a certain kind of a range where it's kind of the most flat. It's kind of the most flat, and that's actually around 80, between 80 to 80 to 90, right? 85 dB. Okay, it's not actually shown here, but at around 85 dB, it's been kind of identified, right, by the standards organizations and engineers all around the world. 85 dB is roughly where our human hearing is, our frequency response is most flat, right? So that's why we see recommendations when we mix, right? We mix at 85 dB SPL, right? So, right, that's very, very important, because if you calibrate your listening when you are mixing at that level, so every time when you mix, every time when you are working on something, or even when you're, I would say, even if you're writing, or even if you're arranging, right, if you calibrate your listening to that, you always hear the frequencies at a much more consistent level. Yes, all right, and I'll talk a little bit more when we get to the week when we do the mixing lah. Okay, I'll cover this a little bit more. Now, a few other things, observations we can also kind of hear. Looking at this curve, right, also tells us a couple of other things as well. Can you see where it dips down? Where it dips down towards the lowest level? Okay, so this lowest level here tells us that's actually the frequency where the human hearing is most sensitive at. And guess where that frequency is? Can you guys look? Can you guys see? Where? 2, 3, 4K. 3K to 4K range. And guess what? So that tells you that's where the human ear, that's the range of frequencies where human hearing is most sensitive to. And why is that actually? It's a very good reason. Why did the human ear evolve to be sensitive to that frequency range? Very, very simple, right? That is kind of the frequency range when a baby cries, or when a small kid cries. Okay, that's the presence, peak, for example, so to speak, for the human voice. So we've evolved it. That's our most sensitive frequency, because that helps us identify, it helps us identify the sound that's coming up from another human being, right? Be they trying to communicate with you, right, using words, using language, or in the case of a baby infant crying, right, they're trying to communicate that they are hungry or they are not happy or something like that. Okay, right? It's a very, very natural and a perfectly good reason why. So having this knowledge also helps lah, right? If you want to make something sound a little bit more to cut through, right? If you want something um uh to be a little bit more cut through, let's say a very busy mix, yeah, that's maybe a frequency which you can, right, boost, right, that 3K, 4K range. Well, of course, not too much, right? Again, too much of everything will make it sound harsh lah. All right, cool. Right, that's a lot to digest, I know. Okay, let's move on to the next one, right? By the way, all these slides are I make it available to you guys, all right? So I put a link, right, which you guys can always download the PDFs for your own reference back then, okay? Right, so let's move on. Next, let's take a look. So when we talk about loudness and intensity, so this is the kind of the general loudness and the amplitudes that we encounter in everyday life, all right? It's a little bit small, okay, but again, when you go back, all right, you can download it and you can look at it a little bit clearer. So let's go down. Let's start from the bottom, right? Let's start from the bottom lah, right? So your threshold of hearing is 0, okay, right? We refer it to as approximately as 0 lah, okay. So now 0 here is not really a 0. I think and I won't go into the scientific definitions of how or why, but 0 dB would measure if you, let's say, take a feather, all right, and you hold it like a few cm off, you drop it, it generates a sound level of roughly 0 dB SPL. Now, okay, so that's your threshold of hearing. That's kind of the softest sound that you can hear, right? The human ear can hear. So let's say you have some leaves, right, rustling in the distance, right, on a cold autumn evening. Okay, we don't have autumn here in Malaysia lah, okay, but just imagine lah, you have some leaves, right, in the distance, okay. So that generates a sound pressure level of about 10 dB. Now, when you go to a broadcast studio, okay, like a TV studio or a radio station, the sound pressure level, all right, the standards inside a broadcast studio is around 20 dB. So it's really, really quiet. When you go to a recording studio, right, the standard actually is a little bit higher, right? It's about 20 plus 30 dB lah. We round it up to about 30 dB. Now, when you go to a library, okay, all right, a different library, I think is different lah. Who goes to library nowadays, huh? Right? There's still people, right? Actually, you'll be surprised. There's actually still a lot of people who goes to a library, you know, right? That's why it's still important. So a average library, right, the ambient noise, the sound pressure level, all right, about 40 dB. Now, if you go to a living room with soft TV music, right, for example, outside there in the waiting room before you guys come in, right, if the TV is on, it's very, very soft, that's about 50 dB. Okay, so normal conversation, okay, if we talk a little bit normally, I'm actually talking a little louder because I'm projecting. So normal conversation is roughly about 60 dB, okay. So now when we move to a vacuum cleaner, right, a vacuum cleaner, that goes up another 10 dB, right, that goes about 70 dB. Okay, let's go next. A busy roadside. Okay, let's go to a very busy roadside in the middle of town, in the middle of city. Okay, you get about 80 dB. Right. Then you're standing on that busy roadside. Suddenly got one large truck passing by. One large truck passes by. Okay, that one sometimes you get about 90 dB. Okay, so yeah, you were getting in a truck, then you're walking, then you decide to go down to the MRT. Okay, right. Depends. You have two choices lah. Okay, imagine you're playing a game. Okay, either you want to go down into the subway, right, or you want to go into a disco or pub. Okay, but now disco and pub all not open, cannot open. Okay, all right. So if you go to a subway, for example, and then the train is passing by, you will get about 100 dB. Okay, now let's get on the train. All right, let's get on the train and let's go take the train, take the MRT, take the LRT. Let's go to Bukit Jalil Stadium, for example. All right, and then we're going to a rock concert, or maybe you're taking a train, you're going to airport lah, right? Right, and you're at the airport tarmac. This one will get to about 110 dB, right, at a rock concert. Okay, so After the rock concert is over, you go back, all right? You're back on the road again, and then suddenly you see at the side there's JKR or someone is doing some road works, and they have a pneumatic drill, that kind of drill, right? When you hear that drill, you can get up to 130 dB. Okay, 130 dB is approaching the threshold of pain already. If you're not wearing any kind of ear protection, it will physically hurt. Right, your ears will physically hurt if you are listening to sound at that intensity, that SPL level. And then now, for example, let's go back to the scenario of the airport tarmac. If you're an airport worker, for some reason, you are standing at the runway when the jet plane is taking off. I don't know why. Okay, just imagine lah, right? Okay, or for example, you take a microphone, right, to be more logical, and you measure lah the jet engine, right, when it's taking off. You are going to get about 140 plus, okay, dB. Yeah, at this, obviously, at that kind of range, obviously, your eardrums will blow lah, right? If you are there, right? So these are kind of the common sound pressure levels that you're going to encounter in day-to-day life, all right? So just for general knowledge, right? Just so that you can be sort of aware of this. So is again recap, right? Fletcher-Munson curve, your equal loudness contours, right? And roughly the human hearing is most linear at about 85 dB. Okay, so that brings us, that's the end of sound properties of sound, right? So again, you have your pitch frequency, right, which is your first property. You have your timbre, you have your wave shape, which is your second property, and your third one would be your loudness versus intensity. Okay, let's move on to the next topic, the next module.